Hi, and welcome to this two-day workshop. It's an introduction to machine learning for language assessment. My name is Vahid Aryadoust from National Institute of Education of Nanyang Technological University, and I will be teaching this workshop today and tomorrow. I just wanted to remind you that this is an introductory workshop, and my aim is to disseminate some essential knowledge and tools for predictive modeling, specifically focused on regression analysis and machine learning. And I'm hoping that you will be able to use it in your research in language assessment. So the first part of this workshop focuses on the general linear model. It's very important to familiarize ourselves with the general linear model, especially the regression model, because the idea is that if we can do predictive modeling using regression, multiple linear regression, we have a better foundation for doing machine learning. The linear regression or multiple linear regression is used for statistical inferencing, but machine learning is not used for making any statistical inference. Linear regression is linear, as the name implies, but machine learning is nonlinear, and in fact, it's a kind of black box sort of approach to prediction. So while in regression analysis, you know the relationship between the independent and dependent variables in terms of, for example, the slope or the coefficients. In machine learning, you don't have the luxury of knowing how the output will change if the inputs or the independent variables change. The main aim of machine learning is just to be able to predict with a high amount of accuracy your output. Whereas in regression, you not only want to predict, but also want to draw a statistical inference, meaning that you want to generalize from your sample to a population, and also measure the weight of each of the variables that you have in your model, specifically your independent variables, and their impact on the dependent variable. There are some commonalities between the two, so I'll try to focus on those commonalities a little bit to help you understand how you can transition from linear regression model to machine learning. The email has been sent out to you, and I hope that you have already downloaded the GUI software, JASP. We're going to use JASP. JASP is useful, is user-friendly, but I also need to let you know that it only provides with a limited number of machine learning models and functions that are available out there. But I believe for beginners, it's a very useful software, especially its machine learning module, which provides you with the ability to do classification and prediction, as well as clustering. But today we only focus on, in these two-day workshops, we will only focus on prediction. All right, so we will have a break later, a bio break in around 1 hour or so, for about 5 to 10 minutes, and then we will come back to continue the workshop for another 1 hour. And also, I wanted to thank the UK Association for Language Testing, the UK Association for Language Testing and Assessment, or UKALTA, for supporting this workshop. If you're asking me what are the resources that I have used, they're primarily these books. From the left-hand side, the 2-volume books that my colleague Michelle Rackwell and I edited. There is a chapter on linear regression, there's a chapter on machine learning, and many other types of models that have been used for years in the area of language assessment. If you're not coming from the language assessment background, but if you're interested in doing statistical analysis in your own field, and if you're looking for a kind of how to do an applied introduction to those statistical models, well, I would recommend those two books, with apologies for advertising my own books. But there are other two books, Discovering Statistics by Andy Phil, and also Hare and colleagues, who have written this very famous book, Multivariate Data Analysis. The one I'm referring to is the 8th edition. It's a very famous and influential book. So that's just a very preliminary introduction to this workshop and to the resources. And without any further ado, I would like to get started with linear regression. Okay, so I'm sure you are familiar with linear regression if you are in this workshop. And I'm sure, or I just hope, that you have used the general linear model. If you do not typically hear this word, let me just refresh your memory. The general linear model is a big family of models, and its members include t-tests, ANOVA, ANCOVA, MANOVA, MANCOVA, ordinary linear regression, and f-tests. So if you have used a t-test in your research or your homeworks, your assignments, you have already used a general linear model. But today we just want to focus on linear regression. So let me provide you with a formal definition of the general linear model. It's a flexible statistical model that generalizes multiple linear regression to accommodate various types of variables. On the right-hand side, you see a very basic graph in which I have two variables, the x variable on the horizontal axis and the y variable on the vertical axis. And to the left side of this graph, you see that there is a table. There's a table where we've got x, y, and y hat. The y hat is empty, but we're hoping to be able to predict the amount of y by using x. This is basically the idea of prediction. So if you want to formally notate a formula for this regression relationship, it's like the mathematical formula that you see at the bottom of the slide, underneath the linear regression graph. So let me read it and get you through it step by step. As you can see, our dependent variable is a y. All right, so here I circle it so you see what I'm referring to. This is our dependent variable. In machine learning, we don't use the term dependent variable. We use the term the output variable instead of dependent variable. So let me write this down here, output. That's the term that they usually use in machine learning. Now, in regression, we also have something called the independent variable, which is represented by that x over there. In machine learning, the term independent variable is not commonly used. The term that is used is inputs. But I think it will be an overkill to use machine learning for such a simple scenario in which you only have one independent and one dependent variable. In fact, machine learning is much more powerful and usable or useful when the number of your independent variables is larger than one, far larger than one, for example, 5, 10 or so. But of course, we will use a smaller data set for this workshop because I couldn't find a very large data set, honestly. But I think the principles are still the same and they apply to large data sets. Okay, so now let's get back to the linear regression. And I believe this is a very important discussion because later on we will, even when we're using the machine learning approach, we will be referring to more or less the same concepts there. So the independent variable is x. Now the independent variable is multiplied by beta, and I'm sure you know what beta is. It's a slope. If you remember your high school or secondary school math, for example, algebra or calculus, if we have a line, a straight line, we can basically calculate the amount of slope by dividing rise over run. That's delta y over delta x, meaning that if you have 2 points, for example, point A and point B, you subtract their y's, and that's on the numerator, and divide it by their x's, and you'll get the amount of slope. But luckily for us, we don't have to do this because our software packages can easily do that for us, so we don't have to calculate the amount of slope and other attributes or features manually. Another feature which you can see is called the intercept. The intercept is represented by beta 0 right here. And on the graph, you can also see the intercept, which is the point where the projection of the regression line intersects the y-axis. That point that I'm highlighting for you, I hope you can see that. Now, you see that there is a distance between that point and the point of origin, or 0, which has been marked by the 2-headed arrows. The 2-headed arrows is the amount of intercept. In statistical modeling, we can not only estimate that intercept, but also we can also find out whether the intercept is statistically significantly different from the point of origin, which is 0. So later on, when we start our hands-on practice, if you see that the intercept's p-value is significant, it simply means that your amount of intercept is significantly different from 0. It's not 0, and it's significantly different from 0. That's what it means. That's about the intercept. In simple linear regression models like this, the intercept is basically the mean of the y value, or the y variable. So this is basically the mean of the y variable. Okay, now let's move to the slope and see how slope can be interpreted and how we can use it for statistical inference. The slope is, like I said, rise over run, like this. Rise over run. This is how we measure slope. And it basically helps us to measure the association between x and y. For example, as x increases, what happens to the amount of y? Or in some cases, as x decreases, what happens to the amount of y? Does it increase or decrease? And so this is a basic definition of slope, and it provides us with the amount of x, the amount of y if x changes for a specific amount. I'll get back to this and I'll tell you more about the slope, especially 2 types of slopes, which are standardized and non-standardized, or unstandardized, and I'll let you know how to calculate them. Another point to remember, and this point that I'm going to share is important because it also applies to machine learning. So let's focus on this a little bit more. As you can see, we have a regression line, which is represented by those the dotted line. Can you see that? And the dots are around the line. They're not exactly falling on the line. The dots represent the amount of x and y in the box just beside it, in the table beside it. Now, the thing is, there is always a difference between each of these dots and the line. So the distance, for example, between the first dot and the line itself is this much, whereas the second one is this much, the third one is this much, and so on and so forth. Okay, now here's the important point that I wanted to share. The regression line represents that equation at the bottom of the linear regression graph, this one. But it's not perfect. Can you see that? If it were perfect, all of these dots would have fallen on the line exactly, and there would have been no difference, no deviation from the line in each of these dots. So the regression line is basically making some prediction, but the predictions are not accurate. Those predictions are the prediction of the amount of y. We already have y in our Excel sheet, which you later will look at, but we want to see if we can identify or establish a mathematical relationship between the amount of y and the amount of x or x's. The amount that is predicted is known as y hat. This is y hat. So it's predicted, and this one is observed. In machine learning, we also have the same concepts. We have a predicted value and we have an observed value. Now, these two values are very important. They're basically used to estimate the amount of error in that linear regression model or the machine learning model that we have used. So I think this is a very important concept, and we need to remember this. Now, these two are used to estimate predicted minus observed statistics, or the other way around, observed minus predicted statistics usually is y minus y hat, which gives us the amount of error. Okay, so let's say our actual amount of x is 6, our actual amount of y is 3 and 6 respectively. Now, this represents the first point, but the point, the y hat that is predicted, is right here, is on the line. So there's a distance between these two. Let's say the y hat here, instead of 6, is around, let's say 5. I may not be very accurate about this, you know, it's not to scale, but let's imagine this is 5. Now, 6 minus 5 gives us 1, and this 1 is the amount of error just for this data point. In the same way, we can find out the amount of error for all other data points. So in the end, we can add up these errors. Of course, we have to, for example, we have to rise them to the power of 2, square them, in other words, because some of these errors are negative, some of them are positive, and if in very basic mathematics, if you add up positive and negative values, they cancel each other out, and we don't want these guys to cancel each other out. So we need to square them, and then we add them up. Then we will get fit statistics, some other fit statistics. Again, like I said, this concept is fundamental to not only linear regression, but also machine learning. And some of those fit statistics will be discussed later today and tomorrow. But if we start talking about them, this is the basic idea. A fit, in other words, is calculated in some way by using some function, some mathematical function that operates based on these two parameters, so these two statistics, the observed y and the predicted y. And finally, there is some amount of error here, which, as I mentioned, is coming from this difference. In linear regression, you have a parameter representing that amount of error, which is also referred to as residual, or you can also refer to it as error. So this is more or less a very basic introduction to the linear regression model and how it works, the different parameters and features of it. Now, I want to wait a second and stop here for a while and see if you have any questions. Please feel free to write it in the chat box. And since the number of people is around 50, if you prefer, you can just open your microphone and ask me the questions before I move on to the next slide. Okay, so there are no questions. Very good. It's either very unclear what I'm talking about or very, very clear to everybody. In either case, Let's move on to the next slide. All right, I was saying that the general linear model is a big family, and basically one of the family members is ANOVA. We are very well familiar with ANOVA. I wanted to also, present this slide to you to remind you that ANOVA is also a regression model. The difference between the previous scenario that I presented and the current scenario is that in this regression, instead of having an independent variable which is continuous, we have a categorical independent variable. And that differentiates between linear regression and ANOVA. For example, we have 3 groups here. I made up this scenario who want to take a language test. And the question is whether the type of breakfast can affect their language test score. So we give the first group omelet, we give the second one ice cream on lava cake, and the third one is fruits and vegetables. As you can see, it's not a good idea to have ice cream and lava cake for breakfast and go to a language test examination room and take a test, because your score drops. And by the way, I just made this up. I mean, this is not science. It's just some kind of funny scenario to, help you get a feel for how ANOVA and linear regression are different from each other. In conclusion, ANOVA uses independent variables that are categorical, whereas the linear regression uses independent variables that are continuous. So far, I have been talking about simple linear regression, everybody. What about multiple linear regression? As the name implies, multiple linear regression has got multiple independent variables. As you can see in this diagram, sorry, no, there's no diagram here. As you can see in this mathematical notation, we have an intercept, we have the first independent variable, which is x1, and it has a slope, which is beta 1. The second independent variable is represented as x2, and of course its own specific slope is beta 2, and so on and so forth, all the way up to beta n xn plus eta or error. So this means that you can incorporate different types of variables, independent variables, in your regression model. But here's a catch. The larger the number of your variables, the larger data set you need. And in fact, the problem of linear regression is that it doesn't work very well in those contexts where you have a large number of variables, regardless of whether you have a large data set or not. Especially some problems can emerge. For example, if you have a large data set, the problem of multicollinearity can emerge, can affect your data analysis. I will discuss multicollinearity after this. But when you have a large data set, chances are that some of these many variables that you have collected might be deviating from normality, and that becomes another problem. Particularly if the error, can you see this error term? This error is not normally distributed, then you're looking at another trouble. Whereas machine learning doesn't have this problem. Machine learning doesn't care about whether your data is normally distributed or non-normally distributed. As long as you have a large enough data set, you can just include any input that you like and any output that you like and see if there's a relationship between them, provided that they are theoretically justifiable. So I wanted to also mention that these slopes, beta 1 and beta 2 and beta n, are also known as coefficients. So if you read a paper or a book chapter and you run into these words, they're basically the same thing. I'm going to use both interchangeably for this and the following workshop tomorrow, so I hope you will remember this. There are two ways of calculating these slopes. And as you will see from the output of JAS, basically both of them are presented in the tables. One of them is standardized and the other one is non-standardized or unstandardized. They could either be positive or negative. Both standardized or non-standardized ones could be positive or negative. If you're asking me what's the difference and how we calculate it, in short, this is how I would explain it to you. The unstandardized coefficients or the unstandardized slopes are calculated just by using your raw data without changing the natural features of your data. Whereas the standardized scores or the standardized slopes are calculated based on standardized scores, meaning that the scores of the variables are standardized first, and then the regression model is fitted into the data. So that's basically the major difference between them. In many of the videos that I have shared on my YouTube channel, I have discussed how you can standardize a variable. Basically, standardization is very easy, very straightforward. What you need is the standard deviation of your variable and the mean of your variable, these two. Then you deviate every data point from the mean of your variable, and then you divide it by the standard deviation to get your standardized value. And after that, if you calculate the mean of your standardized variable, you'll find out, oh, the standardized mean is equal to 0. That's the difference between standardization and non-standardization. Just remember, the way that we interpret standardized and unstandardized coefficients is slightly different from each other. Standardized coefficients are interpreted as follows. For example, let's say the standardized coefficient for x1 is 0.4. Okay, so 0.4 x1. This is how you interpret it. This is standardized, remember. You say that if the amount of x1 increases by 1 standard deviation, the amount of y increases by 0.4 standard deviations. So if x increases by 1 standard deviation, y increases by 0.4 standard deviation. It's about standard deviations. That's why we call it standardized. On the other hand, if you are looking at the unstandardized coefficients, this is how you should interpret it. Just let's assume that this 0.4 is actually an unstandardized coefficient. The way that we interpret it is very similar, but one word changes. To put it simply, the word is standardized, SD. The word changes into units. In other words, if x increases by 1 unit, whatever unit it is, for example, it's scores, it's age, or it's anything, then y increases by 0.4 units, its own units. As you can see, both of them are really useful. Standardized is useful in the sense that it kind of squashes your values and you can interpret it more easily in terms of standard deviations. And it's quite similar to what we traditionally refer to as the effect size. The effect size is basically, for example, in t-tests, is the differences between two mean values divided by the pooled standard deviation, if you recall from t-tests. So those kind of effect sizes are standardized, and so are these coefficients in regression models. But for unstandardized coefficients, I would say the advantage of using them is that you can interpret them in terms of the units, because the units refer to the actual raw data that you were using before. Now, there's one more thing here. In machine learning, with specific focus on neural networks, standardized or unstandardized coefficients do not really exist, because we're not talking about statistical inferencing. These values are useful only if we want to draw some kind of statistical inference. Whereas in machine learning, like I said before, the only concern that we have is whether we can make a good prediction by using a bunch of input variables that go into the model and aim to predict the amount of an output variable, regardless of how they are related to each other, because the relationship between the inputs and outputs in a machine learning scenario is non-linear, unlike a linear regression where you can specify everything in a tidy and neat linear fashion. Machine learning is not like that. All right, so that's about it. I don't think I have much to say in this slide. I just wanted to refresh your memories. So multiple linear regression as a result is a GLM that is used to model the relationships between one dependent variable or response variable and two or more independent or predictor variables. That's how it works. And this is also the same formula that I presented before at the bottom. Nothing really new here. So let's move on to the rest of the story, which is doing regression in two different ways. And I guess this is a very interesting discussion because as far as I'm concerned, the overwhelming majority of papers that are published in language assessment, second language acquisition, applied linguistics, if not all, but the overwhelming majority of them are using statistical model-based methods. But I'm going to show you a new approach today, which falls in between machine learning and regression. And I think that provides a very nice segue to machine learning, which most likely we will be discussing tomorrow. All right, so I want to here stop for a while and see if anyone has any questions or any issues, problems, anything you would like to raise before we go ahead. All right, I see there is something in the chat box. Oh, okay, good to know that. Okay, thank you, Yumin. It's good to know that it's clear. All right, so let's move on. Now the two methods. Two methods of doing regression analysis, everybody. One includes statistical model-based method, which I've already discussed, which you are most likely very familiar with. And the other method is the algorithm-based, something that, like I said, falls between regression analysis and machine learning. And this is, I think, in my view, more important than the usual or the conventional way that we do regression analysis for one reason, because it not only fits a model to the data, but also allows us to test that model on an unseen data set, which is basically one of the distinctive features of machine learning. So let's go through these explanations to make things a bit more formal. The model-based regression analysis is done in this way. The model is specified before the data analysis begins, and then you have to look into the assumptions like linearity, normality, homoscedasticity, and so on, which we'll discuss today, and we will do hands-on on that. And on the other hand, the algorithm-based type of machine learning involves dividing the data into a training set and a testing set. So if you read, like I say, if you read papers in our field, with the exception of those papers where computational linguistics has been used, the majority of regression models don't do this. The authors completely ignore this. I guess I have also ignored that. Also, I'm guilty of doing that too. Not to say, I don't mean that the statistical model-based regression analysis is wrong. No, not at all. It's not. That's not what I mean. The problem with, or one of the limitations of this approach, of this statistical model-based approach, which I have explained just before, is overfitting. I write this down here. Overfitting. And what does overfitting mean? Since this is a workshop and I don't want to be the only person who talks, does anyone like to define overfitting? Feel free to either type it or open your microphone and share your thoughts on overfitting. Nobody likes to give it a try? All right, no problem. Well, so overfitting happens when your model works okay or works pretty well for your data set, for your present data set, but it fails to make any predictions in a different data set. So it only makes sense for your data set. And HL, good. HL is saying the model 2 well trained on training data set, so can't predict. Yeah, very good, very nicely put. Yeah, due to outliers, due to the error. So overfitting is like what HL has written, and I want to just define it in a slightly different way. And I reiterate my definition is that when you train your data, when you train your model, and you fit that model to your data, you'll see that there is a good match between what your model predicts and how your data is behaving. That's great. Let's say you have gotten a very good R-squared value. But now you get the same model and you fit it into a different unseen data set. It's the same kind of data set, but it's different in the sense that the variables are the same, but the people in that data set are different. So if you're predicting, for example, writing scores based on a bunch of variables like age, reading, vocabulary, grammar, and so on and so forth, if you are making universality claims, your model should really hold across different data sets. Otherwise, it just is making prediction for your current data set. That's one of the biggest problems of social sciences. Our models only make predictions in our current data set, and they can't go beyond our current data set. In fact, nobody cares about that, which is terrible, actually. So this is the idea of overfitting. Put it simply, your model works well for your own data. Let's call that training data. But it doesn't work well for a different data set. Let's call that testing data set. That's called overfitting. So if you have an R-squared value of 0.7 for your own data, the training data set, but if you cannot replicate the same R-squared in a different data set, your model is overfitting, it is facing the overfitting issue. This problem is more obvious in model-based or statistical model-based regression than the algorithm-based regression. Why is that? Because, like I said, in an algorithm-based regression model, you divide your samples into training and testing data sets. So the efficiency and accuracy of your model is estimated based on not only its performance on the training data set, but also its performance on the testing data set, as opposed to the model-based data set. But this is something that I wanted you to remember, and as a result, I'm very happy to say that we will be discussing not only the statistical linear regression model today, but also that linear regression that is like a machine learning. And as you can see, we divide the data set into two subsets. One is used for testing, and the majority of the data is used for training. I mean, there are different ways of doing this segmentation. Some people usually cut 80% of it and use it for training, and then the rest of it, which is 20%, is used for testing. Some people prefer to do 70-30. And I don't think it's a good idea to do less than that, like 60-40. Personally, I don't prefer that because I'd like the model to see a lot of data as much as possible so it can make more predictions. As opposed to this approach where everything is used just for I mean, we don't use training and testing jargon here, really. The nomenclature is different. It's just, I don't know, you can just call it training or whatever. There's no testing. In the neural networks, which is a type of machine learning, we have the same philosophy. We cut the data sets into train and test. So 70% or 80% goes to training the model, and the rest of it is used for testing your model. And that's how it is. Okay, there's a question here. Is the segmentation totally random? It's done randomly, yes. It's done randomly. Of course, you do have a second option in which you can create your own testing segment before starting your model training. That's also possible. So you train the model first based on whatever data set you have, and then you find another data set to test your model. In some software like JASP, because we're talking about the GUI, click and go sort of software, you can basically, can JASP do that? I guess JASP can do that if you're doing neural networks, or even SPSS. SPSS can also do that. You can ask JASP or SPSS to only use this portion, certain portion, for training, and do not touch the rest of it, and use the rest of it for testing. In other words, you force that segmentation onto the software, whereas in usual way of doing things, you don't force it on the software. It just chooses it quite randomly. All right, so let's get started with the first type of analysis, everyone, which is linear regression, multiple linear regression. And we want to learn about the assumptions of multiple linear regression first, and do the analysis quickly. Okay, so here's a comment. Use training, testing. Yes, validation data sets. What's the difference between tests? So validation is basically is like testing on a second data set. So it's like testing after testing, which makes your model even more reliable if it's working properly. Because some people are concerned when they're doing machine learning, they're concerned about the model reaching what they call a local minima. Local minima is where the amount of error seems to be pretty fine, but in fact, when you move to a different data set, that amount of error cannot be replicated. The amount of error that you will get will be much larger than the amount of error that you got in your training data set. So in order to prevent this local minima, what they do is to test the efficiency of the model with several different testing samples, one of which is called validation. All right, so assumptions of linear regression, everyone. And these assumptions are not necessary for machine learning, but since we want to do linear regression, we have to do this. Number one, linearity. The relationship between the dependent and independent variables has to be linear, and I'll let you know how to make sure that it's linear or not in the next slide. Number two, independence. It's a very important concept in linear regression. Observations must be independent of each other. Now, if you have longitudinal data, for example, time series, or the sort of data that you would use for repeated measures ANOVA, the Durbin-Watson test is used to make sure that the data is independent. But if you don't have longitudinal data like what we have today, which is not longitudinal, then the Durbin-Watson test is not usable. The third assumption is homoscedasticity. I think some of you, because I saw some of your names are familiar, who have taken a course on research methodology in applied linguistics, do remember the concept homogeneity of variances, and I'm sure the rest of you also are familiar with it. So homoscedasticity is a very similar concept to homogeneity of variances, if the term is very weird and strange. In repeated measures ANOVA, the analogous assumption is the assumption of sphericity, if you recall. So for multiple linear regression, homoscedasticity refers to the following. The variance of the error terms is constant across all levels of the independent variables. And how do we know that? There are different ways of testing for this, and I will show you how to do that in the next slides. And finally, normality, everyone. This is a very important concept, and unfortunately, it has been misunderstood by many authors. We assume, those authors assume that normality refers to the normality of the data. No, the normality is not an assumption. Normality of the data is not an assumption of linear regression. It's the normality of the residual that is the assumption of the multiple regression analysis, or the assumption of normality of residuals basically applies to all members of the general linear model family. It's basically the E or eta or epsilon, how do you read that? The error in the regression model that must be normally distributed rather than the data. Now, I do not deny that if your data, your raw data is not normally distributed, that can somehow affect your regression model. Sure, it can happen. But that is not a big concern as much as the lack of normality of your error is. And finally, multicollinearity. In fact, lack of multicollinearity is an assumption of regression. Multicollinearity is defined as follows. Independent variables are not highly correlated with each other. So it just basically is the correlation between your independent variables. If it's too high, then one of them is, is redundant. Because if you get, for example, a correlation of 0.9 or 0.95, then one of these two variables is redundant because they're almost the same thing, statistically speaking, of course. All right, so how do we do these things? And please get ready for doing some hands-on. Number one, we do a linearity check by looking at some scatter plots. Independence, of course, it doesn't apply to our workshop today, but if we had longitudinal data, you would use Durbin-Watson tests. Homoscedasticity is done through, for example, checking the residual plots and some other tests like the White tests and Bruch-Pagan tests. The normality of errors is checked through, for example, the QQ plot, quantile plot. And by using the good old skewness and kurtosis, you just need to calculate the errors, just like a variable, not manually. The software will do that for you. But I should say, unfortunately, JASP doesn't save it. So if you want to save the error of your regression model, you got to use a different software like Jamovi. Jamovi is also free software, so you can use that easily. Anyways, then you can run the skewness and kurtosis analysis on that variable, and you can determine whether your data, your residual data is normally distributed. And finally, multicollinearity can be measured through different ways. The correlation analysis that I mentioned earlier is one way. Another way is, and some authors use this, is by looking into the variance inflation factor, or VIF, and its inverse, which is known as tolerance. Okay, so let's do this one by one, and also make sure that we do some hands-on. Let me see if there is, okay, there are some questions here. Evaluation is more like our daily homework, and testing is more like the final exam. Okay, that's an interesting way of putting it. All right, so everybody, I would like you to open your data set now. Your data set is, which one should we start with? Let's start with number one. I'm sure you have received the email. as my colleague Lynette has sent to you. Please open the first data set, which is regression versus machine learning. Let me also share my screen. I think at the moment it's only my slides which is shared. So okay, can everybody see Jamovi on my computer? Okay, great, very nice. All right, so this data set, which I have sent you, is a simulated data set. It was simulated based on an actual data set, so it's not all fictitious. Now, what you see in the analysis on the left side, if you have installed JAS, you can just easily open it. There are several regression analyses, and one regression analysis which is done in the way that machine learning is done. I've also just done descriptive stats. You probably don't see descriptive statistics in your tabs, but that's okay. You can just do it later today. And correlations. I did these two analyses because I wanted to make sure that the assumptions of these are met. Okay, everyone, so let's get started with the first regression analysis. Feel free to do a whole new set of regression analysis on your own, but every time that you find any problems and issues, you can just refer back to this side of your data set. So the first analysis I conducted was linear regression using the inter method, and I'll explain what inter method is and why we use it. Okay, how do we do this? You gotta install, if you haven't done so, regression on the upper toolbar by clicking on this plus sign. And if you cannot see regression there, you have to just find regression somewhere, or anyway, if you can't find it. And for machine learning, in the same way, please find that and just click it, right, like this one. There are many other cool things about JAS, which you can also install and try later. So we just need machine learning and regression. Okay. Now, the next step here, everybody, is to make sure that the assumptions are met. Some of these assumptions are met only after we have run the analysis. I mean, we cannot check it before doing the analysis because they're embedded in the analysis itself. So let's go step by step. We have to toggle back and forth between the regression analysis and descriptive stats and correlation statistics in the JASP itself, just giving you the heads up. Okay, the first assumption is linearity. As I mentioned before, linearity is one of the important assumptions of regression, linear regression, but it's not an assumption of it's not an assumption of machine learning, especially neural networks, artificial neural networks. Okay, there are different ways of making sure that your data is linear and there are no curvatures. One of the useful ways is to create this plot. This is created in the regression menu, in the regression menu itself. Remember this plot, please. It's very important because it's going to function in different ways for us. In this regression plot, we are plotting predicted values. Do you remember what we called predicted values? It's a pop quiz. What do we call predicted values in a regression model? Yeah, but there was a term for it. There was a mathematical symbol for predicted values. Yeah, good, y hat. Awesome. So predicted values are y hats. Okay? And we plot them against standardized residuals. Do you remember how we calculate residuals? How do we calculate residuals? Very good, that's also correct. Predicted minus observed, which means y hat minus y, or you can put it the other way around, y minus y hat. Well, it's done automatically for you. Just I'm sharing this with you just in case you want to know what is going on under the hood. So this is error. So the error is eta or epsilon or e, whatever, however you read it, and the y hat, then they're plotted against each other. The violation of linearity occurs if you see a curvature. You can see that curvature, right? If you can see curvature in this data set, this means trouble. This means your data is deviating from linearity. How do we make sure that we don't have this problem in our JAS analysis? Let's go back to inter, everyone. Okay, so these variables were all on this side. I moved writing just by clicking on it and clicking on this arrow to the dependent variable. This is also known as the output. Then there are some methods here: inter, backward, forward, awkward, stepwise. I mean, awkward is not a method, obviously. And covariates and factors. I have got covariates here and factors, and I'm sure you know the differences between covariates and factors. Well, let me ask you, what is the difference between covariates and factors in regression? Can anyone tell me? I'm waiting. Okay, the difference between them, everybody, is the covariates are continuous variables, simply put, whereas factors are categorical. So a variable like gender would be viewed as a factor. And if you want to regress writing on gender, you got to move gender to the factors box. But the rest of them are basically continuous. They're not categorical, and they're treated as covariates. That's simply the difference between covariates and factors. And one more thing is that in a regression analysis, remember, we calculate or we compute the effect of these variables one at a time on writing while controlling for the effects of the other two variables. For example, if I want to figure out the effect of grammar on writing in this regression model, I will be controlling for the effect of vocabulary and reading. And in the same way, if I want to figure out the effect of reading on writing, I will have to control for the effect of grammar and vocabulary. And this is done automatically by the software itself. And if you want to take a look at what is going on under the hood, watch my videos. I have explained these in a lot of details, and I have showcased how that controlling is exactly done. And what does it mean exactly when we say we need to control for the effect of other independent variables when you are looking into the effect of that specific independent variable on your dependent variable. Okay, now let's not get carried away. We're basically looking for that plot. You have to scroll down to the plot section, and as you can see, there are different types of plots. What do we want? We want residuals versus predictive. Click on that. If you like, you can also get residual diagrams because it shows you the normality of your residuals. So you will be checking two assumptions at the same time. Standardized residuals, of course. And finally, QQ plot standardized standardized residuals as well. So I'm going to scroll down on the output and take a look at residuals versus predictive. Question, based on what I just mentioned, do you think that the assumption of linearity is supported or not supported by this graph? Since you already have the data in front of you, I'm going to present the slide once again so you can compare this with what I am displaying. Do you think linearity is supported? Oh, that's a big no. Okay, linearity is not supported. Yes, no, yes. Okay. If we do this democratically, we have got 3 yeses against 2 no's, so yeses will win. Supported. Okay, oh, there are more yeses. All right. Good. Yeah, residuals are fairly evenly distributed around 0. Good. So there is no pattern in the residuals, if you notice. It's just like a gunshot, if I may use that term for this workshop. You don't see any specific patterns. There's no curvature. There is no specific pattern that you would be able to, something conspicuous that you'll be able to observe. So I would say the assumption of linearity here is met. Pattern here. So the dots are scattered everywhere without having a specific pattern. Okay, so this is not too bad so far. So far, so good. And if you like, you can also look at the second assumption just to figure out whether the errors or residuals, recall that the 2 terms are used interchangeably, are normally distributed. So I don't want to get into the discussion of normal distribution because it's basically a given in this workshop. But do you think that this is the normal distribution, or do you think it's deviating significantly from normality? Write it in the chat box, please. Visually, no. Okay, no meaning no deviation from normality, right? Meaning that it is normally distributed. Right, good, normal distribution. Cool, yeah. It looks like a bell curve shape, as you can see, slightly skewed. I agree, slightly skewed to the left side. It might be slightly negatively skewed because the leg is on this side, towards the negative side, but still, it's definitely not a big deviation from normality. So I would say the assumption is met. Again, let me reiterate that the assumption of normality applies to residuals or errors rather than the data. QQ plot residuals. Why is it that the QQ plot is not? I'm not sure why the QQ plot is not outputted. That's the strangest. Okay, let me just sometimes. Okay, it happens. Okay. Click on, click. At some point, I think the QQ plot should appear. Okay, there may be a problem here, but anyway, we do have QQ plots, and I hope that we can find them later. Scroll right. Okay, let me see. All right. Okay. Good. Okay. Okay. This is much better. Good. Okay. This is a QQ plot. Quantile. If you're asking what is Q, quantile plot. So a quantile is a measure is a statistical measure that divides the data set into several segments, depending on what quantile you're looking at. For example, a 25% quantile means that 25% of your data falls below your that point. Another example, if a data point falls at the 50% quantile, it means that 50% of the data falls below that data point, and so on. So the theoretical quantile is plotted against standardized residual quantiles. So you would assume that there is a perfect correlation between the standardized residual quantiles and theoretical quantile. And that perfect correlation is represented by the line. The data should fall exactly on the line. There's a slight deviation on top, which honestly I wouldn't be too much worried about, because linear regression is really rigorous when it comes to deviation from normality, but this is not a huge deviation from normality. So I would assume that this is another indication that the data is normally distributed. Remember that the residual is normally distributed. Okay, so I have already looked at linearity. I've already looked at, we're not going through this. I've already looked at linearity and normality. Now let's move on to the second assumption, homoscedasticity. Homoscedasticity can also be basically examined on the same graph which we were looking at, in which you plot predicted values against standardized residuals, pretty much like what we did. So the evidence that was presented before not only supports the linearity of your data, but also the homoscedasticity of your data. That's a good thing. Now, sometimes homoscedasticity is compromised. The counter nomenclature is heteroscedasticity, which means that this spread of data points has got some sort of pattern. If you look at this, see, it's pretty much like a skewed sort of data. Is skewed towards this side, towards the negative side. And even the data at the bottom is also skewed towards this side. So which indicates that homoscedasticity is not held, is compromised somehow. So we're looking at a problem here. This is another way of looking into homoscedasticity assumption. So I'm going to go back to our data set and see if you feel that this also supports homoscedasticity or not. Yes, very good. Yeah, I agree. Very good. So it not only supports linearity, but homoscedasticity. So if one of them is supported, it also provides some degree of support for the other one. But there are other better ways of looking into homoscedasticity. Here is another way. Okay, I'm going to skip this because this will take quite some time. But we discussed this as well. I think I got ahead of myself, but we have already discussed this. So it's about normality. I'm just trying to find other ways. Okay. I guess they're not in this slide. Sorry, they're not in this slide. But anyway, we have enough evidence now that the data is not only normally distributed, but also it meets the assumption of linearity and homoscedasticity. Now we can move on to this to the fourth assumption, which is multicollinearity. I have discussed this before very briefly, and I said that one good way of looking into multicollinearity is to use correlations. So let's do that. One way is therefore using correlations. Let's do that. Go through your data set again, click on regression, click on correlation. All right, did you click on it? So I have already done that right here. So what you would need to do is to figure out whether there is a correlation between your independent variables. So I'm going to move writing out of this equation really, because multicollinearity is not about the correlation of your dependent and independent variables. It's only and only about the correlation between your independent variables like this. So we can look at the correlations one at a time. Oh, what happened? Sorry, it jumped. Okay, here. All right, multicollinearity is present when you have a high correlation between your independent variables. And the question is, what do you mean by high correlation? How high should that correlation be to support the presence of multicollinearity and indicate a problem in the data set? Does anyone have an idea about that? .7, yes. 0.7, that's what a lot of people agree on, 0.7. Some people are more liberal when it comes to multicollinearity, and they would go for 0.8 and even 0.9. Because if you have got 0.7, the correlation of 0.7, it means around 49% of the variance is in common between the two variables. So if you go by that logic, 49% of variance in common does not mean that these two variables are exactly the same. It means that 51% of the variance is not in common between the two. So they have more difference than similarity. Now, if you reach 0.8, it means 64% of variance is common between the two. So it becomes a bit challenging for us to differentiate these two variables from each other. And if you hit 0.9, it means 81%, because that's the R-squared value, or the coefficient of determination. 81% of the variance that is observed in the two variables is common between the two, which makes it quite challenging to differentiate between the two. So read some literature. In some computational linguistics studies that have been published have established 0.7 as an indication of multicollinearity, whereas in other fields you can see 0.8 and 0.9. I leave it to you to make an informed decision. If you're asking me, I would say anything above 7 is a bit suspicious. Do we have anything above 0.7? No. And that's a good thing, right? Which means that the lack of multicollinearity is supported, but that's not everything. Well, basically, multicollinearity test is also run in a different way in Jamovi, in JASP. In fact, there are two other ways that JASP uses to run the multicollinearity test. And what are these ways? The first way is here under statistics, everyone. If you click collinearity diagnostics, and if you scroll down, call it here, you'll get this collinearity diagnostics table. And another way is if you look at the coefficients, where is that? The coefficients table here, this coefficients table, there are two other statistics, tolerance and VIF, which are also used for testing multicollinearity. In fact, these two are rather commonly used in applied linguistics and language assessment. So I think we gotta take a break, like a bio break for 5 minutes should be fine. And after that, we will come back and continue with our analysis. All right, so let's get started again. We were discussing multicollinearity, everybody, and I mentioned that there are several ways of doing multicollinearity. One of the ways that is unique and is done in JASP, not in many other software that I have worked with, is this sort of multicollinearity analysis. I don't know if you guys have seen this, but I haven't encountered this many times in the past. So this is a very special bonus that using JASP offers to you. So how do we read this table? I don't know if you are familiar with principal component analysis. We don't want to get into details of principal component analysis, but in such an analysis, you divide your data into several dimensions, dimension 1 all the way to 4. Each dimension has got eigenvalues, and based on that, you can also calculate the variance proportions that is in each of those dimensions, which is explained by your variables. Now, what should we really look at in this table? Not to confuse ourselves, I believe the most important thing that you can look at here is the variance proportion, this section. Let me use my pencil again. Okay. This portion first. Have a look at this portion. This represents how much of the variance of each predictor's regression coefficient is associated with each eigenvalue, right, in this column. So how do you interpret it? Look for some rows that have got 2 or more variables that have high proportions of variance. For example, let's look at this row, the first row. There is no high proportion of variance. The maximum is 1, the minimum is 0. You see, all of them are equally small. Look at these numbers, and even the intercept is small, which is good. The second row is more or less the same. The only large value is this, but we don't have an equally large value in other cells, like the reading cell, which is pretty small. This one is pretty small. And this doesn't make a big issue because it's the intercept. The most important thing is these 3 variables, number 1, 2, and 3, because these are the variables we're working with, our independent variables. And in the same way, if you look at the third row, readings coefficient or readings variance proportion is pretty large. This one is still negligible because it's smaller than let me write this again. Okay, it's smaller than 0.3. Gosh, this is very difficult to write on. Okay, again, 0.3 is smaller than 0.3, so which is fine. And in the same way, this variance proportion is also smaller than 0.3, which is also fine. So this is an indication that we don't have this multicollinearity. Otherwise, at least 2 of these cells in each row, 2 and above, in each row would have been large enough, for example, larger than 0.3, 0.4, and definitely something like 0.5 would be worrisome. So in this scenario, this portion of the table tells us that we're probably looking at a case where there's no multicollinearity. In addition, add this to the results of the correlation analysis, which we just looked at. So these two provide sufficient, strong evidence that the data is not multicollinear. And last but not least is the VIF, or variance inflation factor, which is calculated by using the R-squared value, of course. And VIF and tolerance are the inverse of each other. So tolerance is the inverse of VIF. What does VIF represent? It measures how much of the variance of a regression coefficient is inflated due to multicollinearity. So it is about inflation. That's why we call it inflation factor. Okay, so we hope that the VIF index is 1 or close to 1, because that would indicate that there is no significant correlation between the predictors or specific predictor and other predictors. But if we're looking at a scenario where VIF is larger than 10, we're looking at trouble, like that. In addition, tolerance, since they are the inverse of each other, should also be small. It should be large, in the opposite of VIF. So when you have got 1, which is the highest amount of tolerance, when the tolerance is high, there is no multicollinearity. Number 1, therefore, is the highest. The higher the better. But if your tolerance value is pretty small, it suggests that there is severe multicollinearity in your variables. So this is a recipe for trouble, like that. And do we have the data in our output? You bet. Here is data in our output. Under coefficients, you are looking at the tolerance and VIF. You remember, I just mentioned that the VIF of close to 1, equal to 1, is the best. And as you see, everything is very close to 1 here, which is pretty good. On the other hand, the tolerance is the opposite of the pattern, which is also indication of the lack of multicollinearity. So in this scenario, for the first analysis, we have enough evidence that almost all of the assumptions without almost, really, definitely all of the assumptions of our linear regression model are met. Let me recapitulate briefly. Those assumptions were these: linearity, independence, because our data is not longitudinal data, so there's no independence, homoscedasticity, normality of errors, and lack of multicollinearity. So now, after checking all of these, we can go ahead and run our regression analysis and figure out whether there is a relationship or association between our dependent and independent variables. We have already done that. So I have done several types of regression for you. One regression was inter, and I'll explain this in a minute, as I mentioned before. One of them was backwards, one of them was forward, one of them was stepwise, and finally, I've also done linear regression with the machine learning approach. For all of these regression analyses, what you need to do is, of course, you need to determine what you want to include in your model. So I want all of these to go into the model, of course. I don't change this. And oh, by the way, I also want to include an intercept. I hope you remember that the intercept is important. The intercept is the amount of y when x is 0. Remember? The amount of y when x is 0, that's the intercept. Now, what kind of statistics do we want to get in our regression analysis? Well, here are the things that we really need to get for our regression analysis. One of them is the estimates. Estimates are coefficients, the confidence intervals, And also, of course, the p-values will also be calculated. The next thing is, if you like, you can also look at the covariance metrics. Vovk-Silk maximum p ratio, I'm not very sure how this may be useful in our case. I don't make my regression too complex. I think I'll just stick with these. Model fit is also important. R-squared change is important, and R-squared value itself, if you like, you can get a descriptive statistic as well, and also collinearity. And I think that's about the statistics. What else do we want to get? The p-value, you can set the p-value at 0.05. And if anything that has a p-value smaller than, here the default is 0.1. I think this is not a very good default value. I would remove it and we'll replace it with 0.05, which means that when you are doing the regression model, basically, if you run into any variable that has a p-value of smaller than 0.05 associated, larger than 0.05 associated with it, just remove it from the analysis. Why is that? Because it does not significantly impact the dependent variable. So there's actually no use for it. Or another criteria could be set based on the f value, but the p-value would be much more useful here. And the plots have already been, designed. I don't think we need to make our regression too complex today. So let's go through these statistics and make sure that we understand them. Before I go through these, I want to share with you an algorithm. An algorithm is a way of doing things. I usually do this when I'm teaching something. Let me go. Okay, here. The algorithm is this. In addition to the assumptions that we discussed, always try to look for these and report them in your results, and I think you will be on the safe side. I don't think that any reviewer, if you are writing a paper or your thesis, any reviewer would ask for more things. What are these things? The R-squared and adjusted R-squared. The RMSE, which is root mean square error. And this is also used in machine learning, everybody. Tomorrow, we will also see this in some of the machine learning models that we will generate. And finally, unstandardized and standardized coefficients. These are the slopes, do you remember? As well as the associated p-values of each of them. So let's see if we can find these. Number one, if we want to figure out whether our model is doing a good job or not, like I said, we got to look at the R-squared value first. Here, the R-squared value is 0.224. And the adjusted R-squared value is 0.216. The difference between the two is, okay, I'm going to ask you guys, what's the difference between the R-squared and adjusted R-squared? Write it in the chat box, please. Does anyone like to answer? Okay, so let me get this. R-squared is different from the adjusted R-squared in the sense that the adjusted R-squared is adjusted for the complexity of the model, meaning that it's adjusted for the number of, yeah, good, the adjusted R-squared remains the same when new predictors are added to model. Yeah, the complexity, yeah, good, well done. It's adjusted for the complexity of the model, meaning that it is not affected by the number of variables. Because as you add more variables to the model, just the fact that you're adding more variables, just the fact that you're making your model more complex can inflate your R-squared value a little bit. But that is not because your model is better. It's simply because your model is more complex. So we want to control for the effect of complexity on your prediction power. How do you do that? You adjust your R-square and you report your adjusted R-square. So you got to present both of them, R-squared and adjusted R-squared. R-squared is also known as the coefficient of determination. If you recall from correlation analysis, there's a coefficient of determination. This is the same thing. And how do we calculate the coefficient of determination? It's like this, everyone. It's the correlation between your y and y hat. So if you calculate the correlation between the two and get the square value of it, you'll get the R-squared. Why does it matter? Because the closer these two variables are to each other, the more powerful your model is in terms of its prediction power. So which means that if your y and your y hat are very similar to each other, they will have a high correlation. If they have a high correlation, they also will have a high coefficient of determination, or R-squared, which is pretty good, right? And that's what R-squared is. In this case, the R-squared value is 0.224, which means that around 22.4% of the variance that you observe in your data is explained by your model, which is not too bad and which is not too good either. It could have been better, especially given the fact that the adjusted R-square is somewhat smaller, which means that part of this prediction power is simply due to the complexity of your model. Anyway, now the next variable is RMSE. You may have not seen this a lot in many papers in language testing, but it's a very useful index. And if you want to go back to the definition, it's generally, let me just look at the mathematical terms. I prefer this really than just reading the definition. You see, it's predicted minus actual, so it's basically y hat minus actual y squared. That's where the mean square is coming from, squared, and then divided by n, because it's average, and then it's root square. This is the root. Again, I would like to remind you of the first slide that I presented, one of the first slides, where y hat was there. So as you can see, the role of y hat is quite important. So it's through understanding and computing y hat that we can determine how well our model is functioning or performing. So if there's a big difference between the two, I'm afraid the denominator will be, the numerator will be pretty large. So if it's too large, the RMSE will be too large too, which means that we have a model which has got a huge amount of error in it. In other words, the y hat, simply put, the y hat that it is generating or is computing for us is very far from the actual amount, which is y. And if they're too far away, they're not similar to each other, the model is not very useful, right? Let's say the actual amount of y is $20. For example, the income based on something is $20, but the y hat is estimated to be $49. Well, you have a regression model for sure, but just look at the difference. $20 versus $49. It's not predicting anything really. That's why the RMSE is very important, and we have to take it into account when you're looking into regression analysis. Okay, other things that we need to look into are the R-squared change. You can also look at that. We have a null model, which is represented as H0. And the null model is basically a model, a regression model, without any predictors. Meaning it's a regression model without any of these covariates. And it's only and only a model with an intercept. If you want to write it down, it will be something like this. Writing equals, writing is y, equals its own intercept, which is basically its own mean, plus error. So intercept is B0. If you want to write it in mathematical terms, it's like this, B0 plus error. This, everybody, is our H0. That's our null model, which doesn't have any predictors. So if you don't include any predictors in your model, and if you just want to predict the amount of writing by amount of writing, by the mean of writing, you will have a lot of error in it, such that the adjusted R-squared is 0, the R-squared itself is 0, the RMSE is much larger than RMSE of the first model that you have calculated, and the R-squared change is quite significantly high. As you can see, the p-value here on the right-hand side refers to, I shouldn't touch this on the screen. The p-value here on the right-hand side refers to whether the differences between the first R-square, which was 0, and the second R-square, which was 0.224, is statistically significant. It is statistically significant. So the two models have statistically significantly different prediction powers in favor of H1. Okay, so I'm going to quickly go to coefficients in the interest of time. I have already discussed tolerance and VIF. Now, for coefficients, as you can see, H0 has an intercept of 12.640. Question: what is 12.60, everybody? 640. What is it? What does it represent in the writing variable? Do you remember? It's the, drum roll please, unit. Now we want to be more precise. Going back to my slide. Response when, yes, good. It's response when exploratory variables, when the explanatory variables are 0. It's true. So when the explanatory variables are 0, that response is the mean. Remember, the intercept is the mean. Is the mean of the y or the writing variable. So if you check the mean score of writing right now, you will see that the mean score is exactly 12.64. Now, in the second model, this mean is adjusted, and I have explained this in quite several videos. I don't really have time to go through it again to explain how it's adjusted, but please watch my latest videos on regression analysis. There are quite a few, so I have explained step by step. Okay, so this is about unstandardized coefficients, and also we have also another standardized coefficient column here. As you recall, at the beginning of this session, I mentioned that unstandardized coefficients are interpreted as follows. If grammar scores increase by one unit, sorry, this is unstandardized. If grammar scores are increased by 1 unit, the writing score increases by 0.563 units. And in the same way, let's say reading. If the reading scores of students increase by 1 unit, the writing scores will increase by 0.358 units. However, this increase due to reading is not statistically significant, as you can see in the p-value column. Even though it increases, it's not statistically significant. That's a pity. On the other hand, the other two variables, grammar and vocabulary, do have a significant impact on the amount of writing, the writing scores, because that's very obvious from the p-values. What about the standardized coefficients? As I mentioned, you got to interpret standardized coefficients in terms of standard deviation unit. So if the grammar scores of students increase by 1 standard deviation, as a result of that, the writing score of students will increase by 0.313 standard deviations. And another example is vocabulary. If vocabulary scores increase by 1 standard deviation, writing scores will increase by 0.143 standard deviations, which is, by the way, statistically significant. And this is another thing that you need to interpret. And for the notified confidence interval, as you can see in these two columns, the lower and upper intervals, you can say that basically the actual coefficients or slopes in a population fall between this confidence interval, which is rather too big, for example, for vocabulary, which means that we may not have a very high precision in these two standardized and unstandardized coefficients, simply because the 95% confidence intervals are too large really here. But here's the thing. Look at the reading row. What falls between the confidence interval is 0, right? Because it's minus 0.069 and 0.784, which means that the value 0 falls between these two. Since the value 0 falls between the two, it simply is an indication that it's not statistically significant. So if you just look at the confidence interval, really, in the first glance, you can quickly figure out whether the p-value associated with those coefficients would be smaller than 0.05 or not. If 0 falls between them, then it indicates that whatever you're looking at is not statistically significant. This applies to any kind of statistical analysis way beyond regression. All right, so and we have done multicollinearity analysis, we have done assumption check, and so on and so forth. Now, what I wanted you to do in the next few minutes is to play around with different methods. We've got we've got backward, forward, and stepwise. Please go through the analysis, and if you like, you can also look at the analysis I have already done and saved. And you can compare the R-squared values between the models that are generated by using different methods. For example, I'm going to do this, and I hope you can simultaneously do that too on your computer. The R-squared value here was, let me note this down, 0.224 for backward models. You will get two models, as you can see, 0.224 and 0.216. Or you can also look at the adjusted R-squared value. For the forward analysis, the best R-squared value generated is also 0.216. And last but not least, forward, backward, stepwise. Stepwise is also 0.216. I'm disappointed. Everything is the same, with the exception of the first analysis. Okay, so why do we use different methods and what do they do? Here is a quick overview of these methods of fitting regressions. Where is that? Yes, here. Yes. The methods are these, everyone. Inter. If you're using the inter methods, you include all the specified independent variables in your regression model simultaneously, regardless of whether they are statistically significant or not. And just because of this, chances are that your R-square value will increase just a little bit, just simply because the model is too complex. So it will increase or inflate your R-square a little bit, even though one or two of those variables may not be statistically significant. When do we use inter? Generally speaking, when there is a very strong theoretical reason why we have to incorporate all those variables. Backward model or backward method, the forward method and stepwise method are useful when we are doing model comparisons. Of course, backward model is not very much used in model comparisons. I mean, you wouldn't read this in many books, statistical books, but I found that in JASP or some other software, backward method of doing regression is done in the same way that forward and stepwise are being done. But strictly speaking, the two methods that are used for model comparison are basically forward and stepwise. So in forward methods, you start by including no variables in the model, and then you look for the most significant variable, and you include that in the model, and then the second most significant variable is found, and then you include that in the model as well. So it's kind of exploratory. You explore, find out which variable is the most significant one, and you include that. Now, in data sets where you've got quite a few independent variables, the method that you use makes a big difference. Again, watch my videos to get a different idea of how other methods of regression analysis are done. And finally, for stepwise method, it's a combination of forward and backward. How do you do this? We add variables to the model one by one, and that's forward selection. But also, we test them at each step to figure out whether any variables should be removed or not. That's like backward going. And we arrive at some models. Sometimes inter gives you the best R-squared value, but we need to use it only if you have a very strong theoretical justification. Sometimes stepwise gives you a better model. I mean, my experience, stepwise has been useful with other data sets, but it turns out that in this data set, the inter method is giving us a better R-squared value. Nevertheless, one of the variables remains non-significant. So that's something that we need to take into account when you're doing analysis. All right, everybody. So I hope you can go through the rest of these sections and take a look at the art as well. Tomorrow, we will begin by looking at the linear regression and in the way that multilinear analysis, in the way that machine learning is done. And also we will delve into machine learning, particularly neural networks, this one. And if you look at the data set that I provided you with, you'll see that I have compared neural networks with regression and so on and so forth. So we have quite a little bit of details which we'll talk about. Now I'm going to stop now and see if you have any questions before we call this a day. We have around 2 minutes left, so if you have any questions, please feel free to ask. Any questions? Okay, so there's a question. Is it possible to get data sets versus CSV files so I can use it? I don't normally use JASP. I haven't converted the data set to CSV, I'm afraid. But you can ask one of your friends to pass the data to you, or you could just use, really, you can just download JASP, convert it to CSV on JASP, and then just do the analysis on it. Sorry, I don't have the CSV. That's the problem. Any other questions? All right, so I ask you a question, everyone, before we call it a day. Do you or have you ever used machine learning for your research or in your publication? Do you have any experience with it? Please write it in the chat box. Not yet. Oh, that's a big no. Okay. Okay, not yet. Oh, there's a question there. In forward method, do we decide the variables? Oh, we don't decide. The software will decide it because we don't do it manually. So it will just take care of everything. But we can establish the criteria. For example, we can establish the criteria based on the p-value. If the p-value is smaller than 0.05, then it will do the job for you. The heavy lifting is always done by the software. Even when you use R, it will be done by R. Very good, nice. All right, so tomorrow we will have the linear regression in the way that machine learning is done. And if you want to have a look at it before the session tomorrow, you click on the machine learning tab and click on linear. So this will be a linear regression in the way that machine learning is done. So tomorrow we will just focus on linear and neural network machine learning. Okay, so this brings me to the end of the session today. Okay, let me spot. I don't know what I did to myself. Anyway, so let me let's just call it a day. Sorry, I got distracted. I did something on my computer. I don't know what I was saying. Anyway, so tomorrow we will discuss those concepts that I mentioned, and thank you for attendance. I hope you found it useful. See you tomorrow. Thank you. Have a great day.